Hello guys, this is a demo about the Ard Dockerization and something I call the verification lifecycle. This is the broader context where the ARD, known as this ready data Dockerization, fits into. So this is table or something figure shows a higher level overview of this lifecycle. I divided this into 5 different steps, or if you prefer, layers. So this is linear. All output of the layers will be the input of the next one. The first one is the verifiable claim layer. For example, this is just like a use case example. There's a certain land steward making a claim on noted practice happened in a given period of time, which is the time of interest on a given land parcel. This is the area of interest. And the time of interest can be defined by 2 parameters, the start date and the end date, like between March and May. And the area of interest can be defined by a geospatial dataset, for example, shapefile, GeoJSON, and these are like polygons we got from the TMAC guys on any other client. These 3 parameters will define this geospatial temporal query, which will be the input of this query layer, where we will access the names of the satellite data products or satellite images which cover our time of interest. So those which were acquired between March and May, and covers our AOI, like overlaps with them geographically, geospatial, The output of the query layer will be this list of these satellite data product names. And this list will be the input of the ARD layer. Oops. So the ARD layer, which is basically a Dockerized production environment to preprocess a satellite data product. So we will input these data products one by one. I just want to point to two very important aspects here. So I call these data preprocessing lineages, which is a defined sequence of preprocessing steps, how the data moves over time. So if we plug one Sentinel-2 tile into this ARD production environment, this Dockerized ARD production environment will perform predefined sequence of steps, which is basically the preprocessing lineage. So we got 2 main core preprocessing lineage. First one is the Sentinel-1 lineage, and the next one is the Sentinel-2 lineage, like data preprocessing lineage. And if you do this, the second very important thing is we do this because of data provenance. We have to certify the integrity of the preprocessed satellite data in a blockchain-like database. We need to trace and keep track every modification made to the original raw data by storing and recording the different levels of the data along with the production environment, trusted third-party environment, which they are processed up. So this is what I call blockchainization. So after processing up one by one these data products, we will have the analysis-ready data, and that can be plugged into a machine learning algorithm. And the machine learning algorithm is like an algorithm such as the Applied Geosolutions Optis algorithm, which will derive this thematic information, whether a field of the TMAC guys, polygon, a land parcel, in a given period of time was tilled or not. It wasn't tilled, because that's at the end. There's the result layer, which we are actually interested in. So the whole execution of it is just because of these yes or no. Whether the field was tilled or no tilled. So let's see how the data products can be queried from the European Space Agency Copernicus Open Access Hub, or the other name of it, the Sky Hub. And this is just a manual querying and manual downloading of the data products, just to show a few attributes, characteristics of these data products, or just features of the process itself. So the other thing which we have here is the QGIS with the Google Maps base map, and here are the TMAG polygons. So this is the area of interest. These polygons are here near Baltimore, Philadelphia, Lancaster. Here's Quarryville. So we are interested. This is our AOI. So I just use this interface at the European Space Agency to Philadelphia to query data products. Here's Lancaster. Here's Quarryville. This is muddy area. So I will draw this rectangle here. This is our AOI, just roughly. Again, this is just for demonstration purposes. And I want to query our time of interest is between March and May. And I'm interested in having Sentinel-1 data products covering this area of interest and covering this time of interest with this product type, and Sentinel-2 with this product type. We'll show all of the tiles and granules which covers the area and the time. Yeah, so see, oops. So the red rectangles are Sentinel-1 synthetic aperture radar data products. Here we are. This is just a visual quick look at the data product. And then the green squares are Sentinel-1, Sentinel-2 data products. I want to access a quick look. Anyway, so the Sentinel-2 tile is a fixed tiling schema, tiling grid. All of the data products are disseminated in this fixed military grid with the reference ID. The reference ID is this one, which is the name contains the reference ID. Tile identifier, this one. While on the other hand, Sentinel-1 has no fixed schema. Sometimes they cut these swaths here. It shifts a bit, so it's not entirely fixed, although it has a few identifier, such as the relative orbit number, and that kind of thing. Well, anyway, these data products contain a lot of other, not just the image itself. This is the structure of it, subfolders, PDF, metadata file. This is Sentinel-1 data products, measurements under the measurement software, and this is the raw dataset, which needs to be preprocessed. So these are the VH, vertical, horizontal, and vertical bands. While the Sentinel-2 data product also has a different structure. Different subfolders, different metadata files, different everything. Here it sounds very slow. So these are the subfolders. This is the metadata file. This is also metadata file. And under the granule directory. Here are the bands where we download the product. This is the whole shebang which gets downloaded like in a zip format. And you can see that this you can see here that the size of this is 800 megabytes. The size of this is around 1.6 gigabytes. So these are kind of data products which we're interested in having, where we use the extent of our fields. So this is called the bounding box, the extent of the field, which can be derived by the field, by this shapefile itself. Just for demonstration purposes, this is what I will test, to have only the extent cut out from the tile itself, because this is tiling grid, tiling schema of Sentinel-2 with the identification codes. And we can download this thing and we'll preprocess the whole tile, but we are only interested in these pixels which covers our fields. But for this demonstration and testing out our ARD lineage, I will use the extent. Now we will preprocess one Sentinel-1 data product and one Sentinel-2 data product using the two different ARD repositories I will show you. So note that we are here. This is the building block, which is just entirely about the preprocessing pipeline, preprocessing lineage. Here we are. The left one is Sentinel-1 data lineage, and the right one is Sentinel-2 data lineage. These rectangles are Dockerized. So these are the steps which are Dockerized by the LSCAN satellite facility for the Sentinel-1 data product. They call it the radiometric tiering correction, RTC preprocessing. And this is the part which is entirely Dockerized by me. And this is the Sentinel-2 data processing data lineage. They use their own data center, the LSCAN satellite facility data pool, to access the images, because LSCAN satellite facility is a NASA DAC, which means it's an official satellite data distributing the archiving center. And at this point, this solution pulls images from the Google Cloud. Here's the repository of the ASF Sentinel-1 toolbox. And here is where we can find under the region science repository, under the S2ARD subdirectory, the Docker container. So this is a virtual machine on the Google Cloud platform. I already pulled the two repositories, and I already installed Docker and built the S2ARD image. And I also tried out the Sentinel-1 image. So let's have a look on the Docker file first. So it pulls some Python repositories of GDAL, and then wget the ASA snap framework, which is functionality entirely used inside this Docker container, and also their own repository. I think it's just for like auxiliary data downloading. And the entry point is the entry point of this is this RTC Python file, which is under the scripts, or no, it's under this SRC thing. So this is a totally stone solid solution to preprocess only a single data product only one way, which is coded, basically hard coded here. So there is no configuration available. The only input which is needed is the granule, the name of the granule, which I was talking about, like querying the data product name and things like that. And just that's the only input, and then you have to go through an authentication to access the data product from the Elscan satellite facility data center. And very easy to run. The only thing you need is to run this bash script. So you will pull the image, and then we will parameterize the thing. So the only thing we need is just the data product name, which we carried here. So let's see which one we would like to preprocess. Oops. Yes, this interface is very bad. So we have a few solutions here. Let's try this one, just randomly. So I have to log in, and I start fetching the granule and everything. Start running this process. So I queried, picked the name of the data product, went through the authentication, and then I started doing this process. And it will output the vertical horizontal, the vertical bands of the Sentinel data product, which was the input, as a preprocessed gamma node. We call the gamma node data product, and the entire SWAT, which will it outputs. So just imagine that we are only interested in a few fields here, and we will preprocess the whole swath. So maybe 1% the data which we are concerned of. So here we are, the process finished. ASF toolbox, ASF RTC toolbox finished preprocessing the Sentinel-1 image. So here, after authentication, it downloaded the granule, did apply orbit, did the calibration, did the speckle filtering, did the multilooking, did the terrain flattening, terrain correction. The terrain correction needed a digital elevation model, so we downloaded the covering SRTM and in NED data product. I think that's where it did. So it was like an initialization step. It's again like a third-party image, which you need to access to do the daring correction properly. And also, it preprocesses the data into a 30-meter resolution. It's again something which at this point is not customizable. And along this way, along the preprocessing steps, there are plenty of parameter to tweak. So I would highly suggest that we should fork this and make it more customizable. Yeah. It has outputted 4 files, 2 image and 2 metadata file. So let's preprocess the Sentinel-2 data product. Let's have a look on the Docker file. So as I said, it's under the S2 Ard subdirectory. The Docker file is based on Ubuntu distribution. So it pulls Miniconda as a Python environment, installs 2 package, GDAL and Python fmask, which is a cloud masking library, and then pulls Anticore, which is the European Space Agency atmospheric correction software. It installs GSUtil to leverage all the command line interface, and the entry point is this ard.py Python script, which we can find again under the SRC subdirectory. This is got inspired by the Alaska Satellite Facility stuff, but I wanted to make it more customizable, because there is not only one way to preprocess satellite image, and other analysis layer would sometimes need different data input. So if we make it more modular, this Docker container can be leveraged in multiple ways. And how we can customize it is with this config JSON file. So the building blocks it can do are the following. It obviously pulls the data product from, as I said earlier, from Google Cloud, and then it runs the atmospheric correction, the Anticore atmospheric correction module. If you flag it false, it will not run the atmospheric correction. And then it runs the fmask, which is the cloud masking module. It's a spatial domain cloud masking, basically. But there are other different sensor invariant atmospheric correction modules, for example, or Maya from SESBio. So there are multiple options to integrate inside this Docker container to make it more modular, more customizable, to have the user decide which module he or she want to run. But obviously we have to, so this is like a standardized chain at this point with customization like this, with this JSON. I also integrated this crop to cut line option, which will crop out the area of interest, from the tile itself, because that's at the end, which we want to plug into the analysis layer, if you remember. So this will output the ARD, the preprocessed data product, and then the the preprocessed data product will be plugged into the analysis layer. So it makes sense to have only the field data which you are interested in to analyze, not the entire tile. Okay. It can be on as well with this, so like the design, if you don't mind, it's like similar to the Airsoft tool. We can run it the same way by giving the name of a tile. So I prefer preprocessing one of these tiles because our area of interest is on the edge of this Sentinel-2 tile. So let's pick just like regular randomly this one, and then start running the process. So the Docker image is already have been built, as I showed it earlier. It's here, so the image is there. I just throw this data product's name into the image container and it starts the process. This is where it started downloading Sentinel data product. By gsutil, and then it started running the atmospheric correction module, Core module, and this will run for like 30 minutes. Sentinel-2 lineage has finished. So where we left it was like here. Core atmospheric correction module was running, and after running the module, we applied the cloud mask, which it generates, because it generates the same classification which can be used to mask out the clouds from the tile. And after that, I also ran the fmask cloud masking, which was like a separate module, and it also produced a separate image, which is like a binary or a non-binary classification layer, and this one was also applied to our bands of interest, and then reprojection and cropping to the cut line and other necessary image manipulation tools, image manipulation steps were carried out to got stacked, cropped, preprocessed, atmospheric corrected Sentinel-2 band. So this is the file name. I do the analysis here. So these are the repositories we have on the virtual machine. And beside the TIFF Sentinel-1 images I showed earlier, there is the Sentinel-2 stacked image. But these are not stacked, these are separate. Every band is separate as a single file, but we can merge them together, and we have like a multi-dimensional image like here. Because we have here, it's just for testing and demonstration purposes, I picked 5 bands for the Sentinel-2 image, and it stacked it. After that, I moved these images under the output and then output directory I created here, just to make it easier to copy from the virtual machine onto my laptop, my notebook drive, because eventually I would like to see them on my end on QGIS. So that's where I was copying the files, and that's where the files are. So this is the 2 Sentinel-1 image, and this is the Sentinel-2 image. As I said, it already got clipped. Here we are. So the cloud masking routine said these are the clouds. These are clouds here. So it's not perfect. Here also has clouds by the end. This is what remained, and we'll reorder it a bit. Oops. Yeah, this one here. Okay. These are the 5 bands, so if this is an RGB image composite, so this is a preprocessed Sentinel to image chip, which outputted by this Docker container. On the other hand, this is the image, the granule, Sentinel-1 granule. You have to adjust these. This is the image, the gamma note image. It's pretty ugly, but the data is there. It's just the, it's just how it looks in QGIS at the moment, but the data is there. So it's not, I just want to point to the fact that we don't need the whole image. I need only these pixels to run. So that's again another point to note, or just like make a remark on, that we have to integrate inside Docker container this after forking the scan satellite facility stuff, because it's not preprocessed enough. It's just a simple preprocessing, but not good enough for our purposes.